If a carpenter or mechanic tries to manufacture a custom part using only a 3D sketch, they run into an immediate problem. Because 3D drawings use perspective to show depth, the true lengths and angles on the paper are distorted. For exact measurements, we use orthographic projection. Shining a light directly at the front of this 3D matchbox leaves a flat, two-dimensional outline, the front elevation. Rotating to view from the top gives the plan. Rotating again captures the side profile, the end elevation. By isolating these three independent flat faces, we remove perspective entirely. The resulting blueprints provide exact lengths and angles, ensuring that what you design on paper matches the physical object perfectly. We can apply this method to more complex objects. This is a stepped L-shaped block. To map it accurately onto a 2D page, we follow a strict set of layout rules known as first angle projection. Everything starts with the front elevation. It is drawn first using thick, continuous black lines and acts as the anchor for the entire page. The next step is placing the top view, or plan. In the first angle system, the top view always drops straight down to sit directly below the front elevation. To guarantee the plan exactly matches the width of the front elevation, we drop faint, thin construction lines straight down. These are called projection lines, and they carry the exact measurements for you. We repeat this process to position the end elevation. We pull horizontal projection lines across from the front elevation to frame an empty space on the right side of our drawing. Pause the video for a moment. Look at the horizontal lines we just extended. Based entirely on that frame, what is the exact height of the end elevation? It is identical to the front elevation. Because the projection lines drag the height directly across the page, you do not need to measure the vertical height a second time. Trusting these faint lines creates an interlocking, mathematically accurate layout where every view is locked to the exact same scale. Engineering parts are rarely solid blocks. Look at the groove cut into the bottom of this L shape. When the block rotates back to the top view, the solid upper surface entirely blocks that groove from our line of sight. If a structural feature exists, it must be mapped on the blueprint, even if it is physically blocked from your current view. To show a hidden detail, we draw neat dashed lines across the plan view to mark exactly where the invisible groove sits beneath the surface. Mapping hidden details prevents manufacturing errors. It tells the mechanic exactly where to drill or cut inside the block, even when looking at a solid face. Let's test your spatial reasoning by reversing the process. Look at this drawing. If the plan view is a perfect circle and the front elevation is a triangle, what 3D object are we looking at? It is a cone. A circular top-down footprint combined with straight sloped side profiles forms a three-dimensional cone. This checklist summarizes the universal standard for technical drawings. The front elevation anchors the page. The plan sits directly beneath it. You outline visible edges with thick lines, transfer measurements with faint lines, and mark hidden features with dashed lines. Finally, you identify the system using this standard first angle symbol. Review these rules before starting your next drawing. By applying this strict layout protocol, you are using the same visual language as engineers around the world, ensuring your ideas translate clearly into physical parts.